Hello everyone. So today we are here for part 2 of consistent hashing. In part 1 of consistent hashing, I showed you the fundamentals, the ring, the virtual nodes, why modular hashing completely falls apart at the scale, and at the end of that video, I said the real interesting stuff is what happens when you take consistent hashing into actual production systems.
One eternity later.
Yes, it took a while, but here's why. When I went to research, I ended up reading the Amazon Dynamo paper and the Google Maglev paper. And what I found was that engineers at these companies didn't just use consistent hashing. They looked at it, found serious problems with it, and rebuilt it completely in completely different directions. Amazon optimized for the hard drive, Google optimized for the hardware budget, and these two different priorities led to completely different architectures. That's what this video is about. We are covering 6 concepts today. Dynamo Strategy 3, why Amazon threw out the standard virtual node model and what they replaced it with. Google Maglev, a 65,537 slot lookup table where that number being prime is not a coincidence. There's a beautiful mathematical reason for it. Third one is gossip protocol. It it is like how a masterless cluster with no central boss figure out the state of entire network in milliseconds. Fourth one is Phi Accrual Failure Detection. Why simple heartbeat timeout is dangerously naive and what Cassandra does instead. Last one, the Merkle Trees. How two servers holding terabytes of data can figure out exactly which rows are out of sync without transferring a single byte they do not need to. Real papers, real production systems, real engineering trade offs made by engineers with millions of dollars on the line. If you are new here, welcome. I am Harshita Kathuria, Associate Software Engineer at ServiceNow, and on this channel, we go beyond the hype and into the actual engineering behind AI and scalable systems. The real problems, the real failures, and if you haven't watched part 1, link is in the description, or I'll put it in the I button as well. Go and watch that first. The concepts today build directly on it. If you have, let's go. Millions of shoppers generate massive traffic to the shopping cart service. To handle increased demand, autoscaling launches a new server. The new server initially owns random partitions of data spread across hash ring. Every user request now triggers random discretes instead of sequential access. Millions of random seeks overload hard disk (SSD) input-output causing disk contention. As disk performance degrades, the response latency increases. High latency leads to SLA breach, impacting our service reliability. Slow shopping carts for state customers results in abandoned carts and revenue loss. As customer service is everything, this shows up a bigger problem to solve. So let's see how Amazon solved it, evolving through 3 different stages, or we do say strategies. Strategy 1. This is the original virtual node strategy. Every server owns multiple randomly placed virtual nodes on the ring. The partition boundaries are completely random because they are simply the spaces between the consecutive virtual nodes. And that's where the trouble begins. So these partitions are random. The data belonging to the single partition is scattered all across the disk. So whenever a new server joins, the cluster asks, give me the data that now belongs to me. The old server has to jump across thousands or even millions of random disk locations, and those random disks seeks absolutely different input-output performance. On spinning hard drives, random access is painfully slow, and for Amazon, slow meant violating their latency SLA. Amazon's first improvement was surprisingly clever. Instead of letting partitions boundaries be random, they divided the hash space into many equal sized partitions. Now every partition has fixed size. Servers do not own random ranges anymore. Each token maps to one of these predefined partitions. This already makes the disk access much more predictable because storage engine becomes partition aware. Random disk outputs are greatly reduced and overall input output performance improves significantly. But Amazon didn't stop there. Their final design completely separated partitioning from server ownership. Their entire hash space is divided into fixed number of equal sized partitions once, and those boundaries never change again. Servers simply own a collection of these partitions through tokens, and because each partition is permanent, Amazon can store the entire partition as one contiguous file. Now, when a new server joins, there is no need to search randomly across the disk anymore. The old server simply opens the partition file and streams it sequentially. Sequential reads are dramatically faster than random seeks. Bootstrapping becomes faster, snapshots becomes easier, backups become straightforward, and the system scales without fighting the underlying hardware. So the evolution is actually very simple. Strategy 1 optimize the mathematics, strategy 2 optimize the partitions, and strategy 3 optimize the hardware itself. And that's why modern systems like Amazon, Dynamo, and Cassandra moved away from purely random virtual node partitioning and adopted fixed partitions with deterministic token assignment. This is the pattern you'll see again and again in distributed systems. The best algorithm isn't the one that's mathematically elegant, it's the one that works best with real hardware. Okay, let's understand strategy 1 and strategy 3 using a city analogy. Strategy 1 is a city where every new resident causes surveyors to physically erase property lines, tear down fences, and draw unpredictable lot lines in everyone's backyard. Whereas strategy 3 is master plan grid, 10,000 perfectly square, identical lots pre-surveyed. The boundaries never change. When a new resident arrives, the city just opens the filing cabinets and transfer the paper deed. That's how strategy 3 sacrificed the pure mathematical randomness of the original ring to appease the mathematical limitations of the physical hard drive. But what if you are not constrained about your hardware? What if your bottleneck isn't disk input output but raw, unforgiving network traffic? This brings us to Google and the Maglev paper from 2016. Maglev is a software based load balancer operating at layer 4 of the OSI model. Its job is to catch a firehouse of incoming packets from the open internet and route them to the correct backend services inside Google's data centers. We are not talking about shopping carts anymore. We are talking about millions of simultaneous TCP connections, Gmail, YouTube, Google Search, Google Maps, all at the same time. The physical hardware routers connecting the data center to the internet can't handle the complex load balancing logic. They use a protocol called ECMP, equal cost multipath routing. When a packet arrives, the router hashes the 5 tuple source IP, destination IP, source port, destination port, and the protocol, and blindly sprays those packets across clusters of maglev machines. The maglev machines are ones responsible for intelligent routing packets to the actual backend servers. And here's where maglev completely diverges from everything we have discussed. The primary goal of consistent hashing is minimal disruption. When a node is added or removed, only adjacent data moves. Maglev explicitly rejects this priority. Maglev prioritizes perfect load balancing over minimal disruption. Because in Google's environment, if the load balancing algorithm has 5% of variance, you have to physically purchase 5% of hardware just to absorb the spikes. The 5% Google server budget is hundreds of millions of dollars. So they abandoned the ring geometry entirely and invented the Maglev approach, a massive fixed size lookup table instead of ring. Now let's discuss how Maglev hashing works. As Maglev is a fixed size lookup table, so the table size, suppose it's m, and it should be something prime number. It must be a prime number, specifically 65,537. Now the question arises, why prime? Because of how Maglev generates routing paths. Every backend generates preference lists, a permutation of all slots in table. A server A computes mathematically rigorous random ranking of every slot from 0 to 65,536. This permutation is calculated using two hashes. Offset hash, where the server wants to start. Escape hash, how many slots it jumps to make its a next choice. By using a prime number for m, modulo arithmetic guarantees that skip sequence visits every single slot exactly once before repeating. No infinite cycle, perfectly deterministic. The table is populated through a round robin draft pick, exactly like sports draft. A server A claims slot 4000, server B claims slot 12, server C takes its turn. When there is a collision, server A's next preferred slot is already taken. It simply skips down its preference list until it finds an empty slot. This process repeats until all 65,537 slots are filled. Because every server is forced to take turns, no single server can dominate the table. The Maglev paper proves mathematically that the number of the entries for any two backend servers differs at most 1. Variance is less than a fraction of percent. Perfect load distribution. The trade-off. When a backend server fails, the Maglev machine has to rebuild the entire lookup table from scratch. Every slot gets scrambled. A packet for an ongoing YouTube stream that was flowing to server A suddenly gets mapped to server C. Maglev mitigates this local connection tracking table in memory. If packet matches an existing active connection, it routes based on the tracked state rather than a hashing table. But if the Maglev machine itself reboots, the state is wiped. Google decided dropping a microscopic percentage of TCP connections during hardware failures is an acceptable price to pay for perfect load balancing and hundreds of millions in saved capital expenditure. Google optimized their hashing technique for the hardware budget. The recurring theme here is that hardware fails constantly, which brings us to the most vital question, whether you use Dynamo strategy tree tokens or Maglev's prime number permutation tables. How does a decentralized network know that a server has failed? In the traditional centralized architecture, you have a master server, the boss, who pings every worker node every second. When they don't get any response, they mark it dead. Update the routing tables. But Dynamo and Cassandra are masterless systems. There is no boss. All nodes are peers. So how do they agree on the state of network? The answer is gossip protocols. Especially Cassandra introduced Scuttlebutt protocol. Every node maintains the state and it will be propagated. Let's discuss it deeper. Every node maintains a local table of what it believes is the current state of every other node in the cluster along with their versions. Every single second, a node A picks a random peer, say node C, and initiate a gossip exchange. A node A doesn't just say I am alive, it sends the summary of its entire state table. I believe node B is at 12 version, node C it is 9, and node D is at 7. And this information will be compared with node C. its own internal table. Node C knows actually that B is on version 13 and C is on version 20 and D is on version 8. So the data of node A is outdated. So they merge their own knowledge bases. So before A would having that previous table, now it will be changed to the newer version. It is epidemic routing, like a virus. Spreading through population, the math behind gossip protocols proves that the information propagates to every node in cluster with logarithmic speed within milliseconds. A state change on one node is universally understood by thousands of nodes without any central coordination. But sharing state is different from diagnosing of failure. The traditional approach, heartbeat check model. A node A hasn't heard from node B in past 5 seconds. It will flag it will flip the flag from true to false. Node B is dead. The Cassandra paper aggressively attacks this model. What if node B is perfectly healthy, CPU disk fine, but at the top of the rack switch, connection A to B is experiencing a micro burst of congestion. Heartbeat packets get delayed, A's 5-second timer expires, A declares B dead, the cluster panics. Thousands of servers immediately begin migrating terabytes of data to replicate B's supposedly orphaned partitions, blasting replication traffic across a switch that's already congested. Complete network collapse from a healthy node. The Boolean heartbeat is the boy who cried wolf. To solve this, Cassandra implemented Phi Accrual Failure Detector. Instead of outputting true or false, it outputs continuously shifting suspicion phi. It's a score. So let's get deeper into the algorithm further. The Phi Accrual Failure Detector. Instead of outputting true or false, it outputs continuously shifting suspicion score. The algorithm tracks historical arrival times of the heartbeat from every peer. It maintains a sliding window of timestamps. Using this data, it calculates the mean, the variance of network latency, continuously modeling the distribution of arrival times. It's learning the weather of network. When a heartbeat is delayed, the algorithm computes the probability that the silence is just normal variance based on historical condition. The probability is expressed as phi. If phi is 1, then 10% chance declaring the node dead is a false positive. Too risky. We wait. If phi 2, 1% chance. Still wait. If phi 3, 0.1% chance. Cassandra lets their admins to tune their threshold based on their hardware environment, typically set between 5 to 8. The brilliance of Phi Accrual is that it yields to the messy, non-deterministic reality of the physics. It doesn't enforce rigid rules. It calculates the dynamic probabilities, but eventually the math catches up. The server actually catches fire. The phi hits the threshold, the node is pronounced dead. Let's discuss the synchronization problem. If a new or replacement node needs to sync a replica partition, the brute force approach would be sending the terabytes of data between existing node and new node. But this seems too slow, expensive, and even impossible. So, for this such synchronization problem, we need a solution, and it's a Merkle Trees. It's a data structure optimized for and efficient and verifiable and scalable data synchronization. So, these are created from, it's like built from bottom to up. It's a bottom up approach. So, let's discuss every step one by one. So, step 1, hash every individual data row, like cart 101 becomes h1, cart 102 becomes h2, and so on. Once the leaf nodes are hashed, then it creates further parent hashes. By hashing the concatenated child hashes together, like H1 and H2, together forms H12, and it forms the hierarchy repeatedly. Build parent hashes by hashing, concatenating child hashes, and forming combination out of those like H3 and H4 together makes H34. And if we repeat this up by the hierarchy, hashing pairs together level by level, and once it converges to one root hash, a single value that represents the entire partition, it forms the complete Merkle tree. But now if the data is identical, the root hash is identical. If even if one bit changes, the root hash changes completely. This is the avalanche effect. A change in a single bit in row 2, that leaf hash changes and its parent changes and then cascades all the way up. The final root hash comes out completely different even though only one row was touched. Think of it like a resync for databases. Instead of sending a full copy of everything, Merkle sends only what changed, giving you minimal bandwidth, faster recovery, and verifiable integrity, no matter how large the dataset gets. Take a shopping cart example. Four rows, four leaf hashes converging into one root hash. If cart 102 gets updated, only H2 changes, and that change automatically propagates upward through H12 into the root. The takeaway: the Merkle trees gives us compact fingerprint of massive data and precise map to exactly where the differences are. Anti-entropy binary search on differences. So now we have root hashes. Here's two servers actually use them to sync. Step 1. Server A and server B exchange root hashes. If they match, done. Probably synchronized with zero data transfer. If they don't, the data differs and we move to step 2. Fold the tree. Compare child hashes level by level. Matching branch means that entire subtree is identical. Prune it, skip it entirely. If a differing branch means we drill down further into its children. Repeat this until you reach the leaves. This is binary search, but on cryptographic differences. Let's walk the actual example. At level 0, the roots do not match. So drill down. At level 1, the left branches match. Pruned, skipped entirely. The right branch differs. Drill down again. At level 2, the same pattern. One side matches and gets pruned, other side still differs. By level 3, we narrowed it down to the exact leaves. L10 and L12 are different. Everything else has already been proven, been identical and skipped. Only those two mismatched rows gets transferred. And this whole process converges in milliseconds even on massive datasets. Why does this matter? It scales to terabytes and beyond. Because the work is proportional to what changed, not the total size. It converges in logarithmic time. It saves bandwidth by transferring only differences, and matching hashes are mathematically provable, cryptographic proof, not a guess. Compare that traditional sync which sends everything in O of n, and anti-entropy sync sends only the differences of d. D is far and far smaller than n. It's like comparing two huge books instead of reading every page. You compare chapter, summaries, then sections, then paragraphs, only drilling down where something is actually different. Bottom line, anti-entropy ensures replicas heal quickly, efficiently, and with minimal network cost. So that's it for the video. If you stayed till this point, I hope you understand some things better than you did before. And if you want to dig deeper and read the exact research papers, I'll put them in my description box. And if you genuinely like this video, make sure to hit the like button and subscribe to my channel to follow along in the series. See you in the next video. Till then, bye bye.